The 1970s were a turning point in commercial aviation. Air travel was expanding fast, but safety was still catching up. More people were flying. More flights were crossing the same skies. Jets were getting larger, heavier, and more complex. And when things went wrong, the consequences were often massive. In this video, we'll look at the decade that includes some of the biggest disasters in aviation history, the 70s. If you enjoy deep, realistic aviation documentaries, please support the channel by subscribing and liking the video. It helps a lot. On 28 November 1979, Air New Zealand Flight 901 left Auckland on what was sold as a one-day sightseeing flight to Antarctica. The aircraft was a DC-10. The plan was simple on paper: fly from Auckland to the Ross Sea region, descend for low-level views near McMurdo, then return to Christchurch in the evening. On board were 237 passengers and 20 crew. Many carried cameras. For most of them, this was a once-in-a-lifetime chance to see the edge of the world from the window of a jet. The route was not improvised by the crew on the day. It was pre-planned by the airline's navigation section and loaded as a series of waypoints into the aircraft's inertial navigation system. On previous Antarctic flights, that route took the aircraft down McMurdo Sound, with high terrain safely off to the side. But in the hours before Flight 901, the stored coordinates for a key waypoint were changed on the ground. The new track ran not down the middle of the sound, but directly toward Mount Erebus on Ross Island. The crew were not clearly told that the route had been altered. When they checked their printout against the company material on board, the documents in front of them already matched the new shifted coordinates. As far as they knew, they were following the same safe path that other crews had flown before. Hours later, flight approached the Antarctic coast. The crew contacted air traffic services near McMurdo, spoke with personnel on the ground, and began to descend for sightseeing. Everyone involved believed the DC-10 was over the featureless water of McMurdo Sound with open space ahead. In reality, because of the changed route, the aircraft was lined up with the lower slopes of Mount Erebus itself. The mountain is more than 3,700 meters high. The jet was descending toward 2,000 feet. On the flight deck, the pilots and observers were busy looking for landmarks on the ice, pointing out features, and trying to match what they saw to their expectations. Outside, the weather created a deadly illusion. A layer of cloud blended into the white snow of the volcano, removing contrast between ground and sky. This type of sector whiteout can make a rising slope look like level sea ice. The crew believed they were over flat ice with the Ross ice shelf stretching out ahead, while in fact the ice shelf was already behind them, and they were heading straight toward terrain. Whiteout as a formal hazard was poorly understood, and was not something the airline had trained crews to recognize in this context. At 12:49 local time, the ground proximity warning system suddenly came to life. On the cockpit voice recorder, the familiar whoop whoop pull-up alarm sounded, warning that the aircraft was dangerously close to terrain. The crew reacted and began to pull up, but there was almost no margin left. Seconds later, Flight 901 flew into the slope of Mount Erebus at about 1,465 feet above sea level. The DC-10 broke apart and scattered wreckage across the snow. All 257 people on board were killed. Because the crash site was in one of the most remote regions on Earth, there was no immediate help. When the flight failed to return, search aircraft were sent out from New Zealand and from Antarctica. About 12 hours after impact, a United States Air Force aircraft spotted wreckage on the side of Erebus. Helicopters and ground teams were sent in. The recovery operation, called Operation Overdue, became a brutal mission in freezing temperatures and difficult terrain. Wreckage, personal belongings, and bodies had to be recovered from a steep, icy slope under shifting weather. The disaster shook New Zealand deeply and became the country's worst peacetime aviation accident. The first official accident report, led by Chief Inspector Ron Chippendale, focused mainly on the actions of the flight crew. It concluded that the primary cause was pilot error, descending below the minimum safe altitude in conditions where the exact position of the aircraft was uncertain, and continuing at that altitude toward rising terrain. Public debate and new evidence led to a Royal Commission of Inquiry, headed by Justice Peter Mann. The commission re-examined the navigation data, company practices, and internal documents. Mann reached a very different conclusion. He found that airline officials had changed the programmed route so that it now pointed directly at Mount Erebus and had failed to tell the crew. In his view, the crew were never properly informed that they were flying a new track through high terrain. He also criticized the way the airline handled the investigation and famously described parts of its response as an orchestrated litany of lies. The report shifted the main responsibility from individual pilots to systemic and organizational failures in route planning, documentation, and corporate culture. Air New Zealand Flight 901 was classified as controlled flight into terrain, an aircraft that is technically under control with no major mechanical failure, flown into the ground because crew and systems together do not recognize the real position and height in time. After Erebus, airlines and regulators placed far more emphasis on navigation data management, independent checking of company-created routes, and training on visual illusions in polar and snowy environments. Today, almost all of the wreckage still lies on the side of the volcano. The lesson from Erebus remains clear. When an airline changes the lines on the map, but the crew's mental picture stays the same, a modern jet can be programmed to fly perfectly, straight into a mountain. On 24th of June 1975, Eastern Airlines Flight 66 was in the last minutes of its trip from New Orleans to New York. The aircraft was a Boeing 727 with 124 people on board, cleared for an instrument approach to runway 22 left at John F. Kennedy Airport. Ahead of it, a line of thunderstorms sat right across the final approach path. Dark clouds, sheets of rain, and sharp wind shifts were sitting exactly where every arriving aircraft had to pass. Other flights were already feeling it. A large cargo jet had just landed and reported severe wind changes on short final. The captain warned that the airspeed had dropped hard near the ground. A few minutes later, a wide-body jet from the same airline came in to land on the same runway, hit violent turbulence and strong wind shear, and had to go around. Two more aircraft still managed to land. Each report added one more piece of evidence that something was very wrong on the approach to runway 22 left. But traffic continued and the runway stayed open. In the cockpit of Flight 66, the crew knew the weather ahead was bad. They listened to the earlier reports and discussed the severe wind shift on final as they were vectored around the worst radar echoes. On instruments, the approach still looked normal enough to continue. The localizer and glide slope were available. The checklist was complete. The runway lights were somewhere ahead, hidden by rain. Then the aircraft flew into the core of the storm outflow. In just a few seconds, the conditions around the 727 changed. A strong headwind that had been helping the airplane to fly suddenly collapsed. At almost the same moment, a powerful downdraft pushed the aircraft downward. The rate of descent jumped. The jet dropped below the proper glide path. The crew added power, but the engines could not deliver full thrust instantly. Altitude was already bleeding away, and visibility was still poor. At around 4 in the afternoon, Flight 66 struck the approach light structures for runway 22 left, roughly 3/4 of a kilometer before the threshold. The airplane hit several of the tall metal towers, lost parts of its landing gear and wings, and broke apart as it crossed the road just outside the airport fence. Fuel spilled and ignited. Fire spread quickly through the wreckage and into nearby cars. Out of 124 people on board, 113 died. 11 people in the rear section survived with injuries. For a time, this was the deadliest single aircraft crash in United States history. Investigators later gave a name to what had destroyed the flight: severe wind shear from a concentrated downdraft inside the thunderstorm. The aircraft had flown into a small but violent zone where the wind changed direction and strength faster than pilots and engines could react. The official findings pointed to two linked problems. The weather itself created a sudden loss of lift close to the ground. The system around the flight did not fully recognize that this was an extreme hazard that should have stopped further approaches. Warnings from earlier aircraft were passed on, but there were no hard rules, no dedicated low-level wind detection equipment, and no standard training that treated these conditions as an immediate reason to break off the sequence. Flight 66 became one of the key accidents that changed how the industry treats storms near airports. It helped drive research into microbursts and wind shear, led to the development of specialized wind shear alert systems, improved use of weather radar around runways, and new training on how to recognize and escape these events. The lesson from that day over runway 22 left was simple and uncomfortable. In some storms, the most dangerous part is not the lightning you can see, but the invisible wall of wind waiting just above the ground. On 27th of March 1977, Los Rodeos Airport on Tenerife was never meant to be the main stage. Most of the big jets that day were supposed to land at Gran Canaria. Then a bomb exploded in the terminal at Gran Canaria, and there was a threat of a second device. The airport was closed. Flights were diverted to Tenerife, a smaller field with limited space. Within a short time, taxiways began to fill with 747s that normally would never all be there at once. Controllers started using the single runway as a place to park and backtrack aircraft. Among the diverted flights were a KLM 747 and a Pan Am 747. Both were heading for Gran Canaria with holiday passengers on board. On the ground at Tenerife, delays grew. Passengers were kept on board. Flight and duty time limits were in the back of the crew's minds. KLM decided to refuel on Tenerife, which would allow them to go straight back to Amsterdam after Gran Canaria. That decision added more delay and made the aircraft heavy for departure. Pan Am waited behind, still loaded, still trying to get out. When Gran Canaria reopened, everyone wanted to leave as soon as possible. The airport layout was now working against them. With taxiways blocked by parked aircraft, the tower told KLM to taxi onto the runway, roll all the way to the far end, turn around and line up for departure. Pan Am was told to follow onto the runway behind KLM, then leave the runway at the third exit and move onto the parallel taxiway. On the chart, that turn looked simple. On the actual runway in the weather that day, it was not. As the aircraft began to move, hill fog drifted across the field. Visibility came and went in thick patches. Near the threshold, KLM still had acceptable visibility as it reached the end of the runway and turned around to face the takeoff direction. Further back, Pan Am entered a heavy bank of fog. The taxiway exits were hard to see. Markings and lighting were not designed for this mix of traffic and weather. In the cockpit, the crew discussed whether the junction they had just passed was the third exit or whether they should continue. By the time they were sure, they had already gone beyond it and were still on the runway. There was no ground radar to show the controller exactly where each 747 was. The tower could not see the runway through the fog. Everything depended on radio calls and position reports. On the frequency, several transmissions began to overlap. Words were clipped or blocked by other voices. The controller gave KLM its route clearance, which explained how to climb and where to go after departure. It was not a takeoff clearance. The KLM crew read the clearance back. The captain then added his own phrase in English, that they were now taking off. At the same moment, Pan Am tried to say that they were still on the runway, taxiing. Parts of these transmissions stepped on each other and never clearly reached everyone who needed to hear them. Inside the KLM cockpit, the captain released the brakes and advanced the thrust levers. The aircraft started its takeoff roll down the foggy runway. The first officer and the flight engineer were not fully comfortable. On the recording, there are questions and a brief challenge, but the aircraft was already accelerating. Ahead, inside the fog, Pan Am's crew suddenly saw landing lights coming straight toward them. For a short moment, they tried to make sense of it. Then they realized it was a 747 rushing down the same strip of pavement. Both crews reacted in seconds. On the KLM jet, the captain pulled back early to lift off before reaching the other aircraft. On the Pan Am jet, the captain pushed the thrust forward and tried to turn the 747 off to the left and away. The KLM nose did rise and the front of the jet did clear the Pan Am to some degree, but the aircraft was still too low and the angle too shallow. The main landing gear and the engines under the right wing struck the upper fuselage of the Pan Am, tearing open the cabin just behind the cockpit and ripping the structure apart. The collision sent fuel and metal in all directions. KLM's right engines and wing were badly damaged. The 747 stayed in the air for only a short distance, then lost lift, rolled and hit the ground further down the runway, breaking apart and bursting into flames. All 248 people on board the KLM flight died. The Pan Am jet remained on the ground, its right side and upper deck shattered. Fire spread quickly through the cabin. Many passengers and crew near the front managed to escape through openings in the fuselage and moved out onto the left wing, away from the flames. Out of 396 people on the Pan Am flight, 61 survived. In total, 583 lives were lost, which still makes Tenerife the deadliest single accident in aviation history. Later analysis showed that no single failure caused the disaster. Weather, airport congestion, blocked taxiways, the use of the runway as a taxi route, missing or confusing signage, the lack of ground radar, non-standard radio phrases, overlapping transmissions, and the authority dynamics inside the cockpit all played a part. On the tapes, one of the last clear phrases from the KLM captain is simple, a statement that they are taking off. On that day, in that fog, everyone around him understood different things when they heard it. On March 3, 1974, Turkish Airlines Flight 981 departed Paris-Orly for London after a delayed turnaround and heavy last-minute boarding. It was a DC-10, and it was full. The aircraft lifted off at about 11:32 in the late morning, and the climb looked normal at first. Less than 10 minutes later, while still in climb around 12,000 feet, the cockpit voice recorder captured a sudden noise. Air traffic control picked up a brief transmission in Turkish that was partly buried by heavy background noise. The pressurization warning followed, then the overspeed warning. On radar, the aircraft return split and the secondary radar label disappeared. About 70 to 77 seconds after the initial failure, the DC-10 struck treetops at high speed and disintegrated in the Ermenonville forest northeast of Paris. All 346 people on board were killed. The investigation traced the start of the chain to a single door, the left aft cargo door. It was an outward opening design. That matters because at altitude, the pressure inside the aircraft pushes outward. If an outward opening cargo door is not fully latched and locked, the fuselage pressure can force it open with enormous load. On this aircraft, the door could appear secure even when it was not. The external handle could be stowed while the internal latch hooks were not properly in the locked position. The design depended on a precise mechanical sequence. If the latching mechanism was not correctly engaged before departure, the handle and the vent door could still end up looking normal. In this case, the warning protections also did not save the crew. The aft cargo door warning light system could indicate safe even when the door was not fully secured. When the door failed, it did not just open, it separated. The cargo compartment depressurized instantly, but the passenger cabin above it cockpit stayed pressurized for a moment. That pressure differential loaded the cabin floor like a giant piston. The DC-10's cabin floor above that compartment did not have pressure relief vents designed to equalize that sudden difference. The floor structure failed and collapsed downward into the cargo area. That collapse was the point of no return. Critical control cables ran through that area. The severing of those cables meant the crew lost key pitch control. The aircraft pitched down aggressively and accelerated. The crew reduced thrust on the wing engines, but the speed kept building. Control authority was gone. The last part of the flight was not a fight, it was a fall. What makes Flight 981 even harder to accept is that this vulnerability had already been exposed. In 1972, American Airlines Flight 96 suffered a similar DC-10 cargo door failure and an explosive decompression. That crew managed to land, and the event revealed the same basic risk, including floor collapse effects and flight control disruption. Safety recommendations and modifications followed, but the wider system still had gaps in how urgently those fixes were mandated and verified across fleets. Flight 981 became the moment the industry could no longer treat it as a survivable warning. In the days after the crash, regulators moved to force changes, and the design assumptions around cargo door security and pressure relief had to be rewritten. The lesson was simple and brutal. On a wide-body aircraft, a hidden latch is not a small problem. It is a single point of failure that can destroy the airplane in under 2 minutes. On 25 May 1979, Chicago O'Hare was busy with afternoon departures when American Airlines Flight 191 lined up on the runway for Los Angeles. It was a DC-10, full of holiday and business passengers, 3 engines running at takeoff thrust. From the cockpit, the start of the roll looked routine. The aircraft accelerated down runway 32 right, the crew reached rotation speed, and the first officer began to lift the nose. A second later, everything changed. As the DC-10 started to rotate, the entire left engine and its pylon tore away from the wing. It flipped up over the top of the wing, smashed a section of the leading edge, and fell back onto the runway. People watching from the ground saw something they could hardly process: a wide-body jet climbing with one engine missing, and fuel and hydraulic fluid streaming from the left wing. Inside the airplane, the crew lost electrical power on the system that fed the cockpit voice recorder. On the tape, there is only a heavy thump and then a single word from the first officer. After that, silence. The mechanical damage was far worse than one engine gone. When the pylon ripped away, it severed hydraulic lines that kept the leading edge slats on the left wing locked in place. With hydraulic pressure lost and a piece of the leading edge torn off, air loads forced the slats on the outer part of the left wing to retract. The right wing still had its slats fully extended and its engine producing full power. The left wing suddenly produced much less lift. At the same speed and attitude, one wing was now closer to stall than the other. The stall speed on the damaged side jumped above the speed the crew was using for climb. The left wing stalled first. The DC-10 began to roll left, slowly at first, then faster, until witnesses saw the jet partially inverted, with the right wing high and the left wing down toward the ground. There was no time, no altitude, and almost no control authority left. Seconds later, Flight 191 slammed into an open field just beyond the airport, broke apart, and exploded. Large pieces of wreckage and burning fuel tore into a nearby trailer park. All 271 people on board were killed, along with 2 people on the ground. The investigation quickly focused on a deeper question. Why had the engine fallen off in the first place? The DC-10's design allowed the engine and pylon to be removed separately using a precise procedure. At American's maintenance base, to save time, a different method had become normal. Crews used a large forklift to remove the engine and pylon together as a single unit, lifting them off the wing. It was faster, but it left almost no margin for error. If the forklift was even slightly misaligned, the load could bend the hidden fittings that attached the pylon to the wing. On the accident aircraft, earlier maintenance had already damaged that structure. Cracks developed in the pylon. They were not fully detected or repaired. On Flight 191's takeoff, under maximum thrust and rotation loads, the weakened mount finally failed. The pylon broke, the engine separated, and the chain of aerodynamic failures began. For the public, Flight 191 became a symbol of the DC-10's problems. For investigators, it became a textbook case of how a maintenance shortcut can become a structural failure years later. Regulators banned the forklift method, tightened the definition of major repair, increased oversight of heavy maintenance, and required design changes so that damage to a hydraulic line could not so easily let the slats retract and unbalance an entire wing. For the families in the city that watched a fully loaded DC-10 roll over and fall just outside the airport fence, it remained something else. Proof that in the late 1970s, even a routine takeoff on a clear day could still hide the deadliest kind of risk. On the night of 29 December 1972, Eastern Airlines Flight 401 left New York for Miami. It was a wide-body trijet, a new Lockheed TriStar that represented the cutting edge of its time. The flight down the East Coast was smooth and uneventful. Late in the evening, the jet began its descent toward Miami. The crew set up for landing, briefed the approach, and extended the landing gear. Then, a very small detail changed the entire night. The green light that confirmed the nose gear was locked down did not come on. At first, this looked like a nuisance, not an emergency. The crew cycled the gear. The light still stayed dark. They told approach control they needed time to sort it out, and were cleared to leave the approach and hold over the Everglades at 2,000 feet west of the airport. The jet leveled off in the dark night sky. Below, there were no city lights, only black water and marsh. Inside the cockpit, everyone's attention moved toward that one tiny panel with its single missing green light. The captain asked for the light assembly to be pulled out so they could check the bulb. The first officer kept the jet pointed roughly toward the holding fix. The flight engineer left his seat and went down into the equipment bay beneath the cockpit to look through a small window and see whether the nose gear itself was actually down. At one point, the captain told the first officer to put the aircraft on autopilot while they worked on the problem. On the surface, it sounded like a safe, sensible step. Let the automation hold the airplane steady while the crew troubleshoot the indicator. But something subtle happened at the same time. As the captain turned and reached, he bumped the control wheel. On this type of autopilot, that gentle forward input was enough to change modes. Instead of holding a fixed altitude, the system began to follow the slight nose-down attitude it sensed. The jet was still under autopilot control, but it was now set to maintain a gentle descent instead of level flight. From inside the busy cockpit, nothing obvious changed. There was no loud warning, no sudden pitch, no alarm that shouted, "You are no longer level." The airplane simply started to sink, very slowly. For a while, no one noticed. The ground below was black and featureless, offering no visual cue. The crew were talking about the light assembly and the nose gear. The flight engineer was still below the floor, away from his instruments. An altitude alert chime sounded when the aircraft drifted a few hundred feet below 2,000, but the speaker for that chime was mounted near the engineer's station. At that moment, his seat was empty. Up front, the captain and first officer were still focused on the gear problem, assuming the jet was holding altitude like it always did. Over the next minutes, the widebody dropped lower and lower over the swamp. On radar, the controller eventually saw that Flight 401 was no longer exactly at its assigned altitude and called to ask how things were going. In the cockpit, there was a brief exchange as the first officer suddenly realized that the altimeter did not match what they expected. By the time the words were out, it was already too late. The nose came up slightly as they reacted, but the airplane was only a few seconds from the ground. Flight 401 hit the Everglades about 18 miles short of runway 9 left. The left wingtip struck first, then the left engine and landing gear, cutting long scars through the sawgrass before the fuselage broke apart and scattered across the shallow water. The jet was still moving at high speed. Sections of cabin tore open, seats were thrown free, and people were flung into the swamp in the dark. Out of 176 people on board, 101 died and 75 survived with varying degrees of injury. For those who lived through it, the night turned into a long struggle in cold, fuel-soaked water until rescuers in airboats and helicopters could reach them. Investigators later recovered the recorders and rebuilt the last minutes of the flight. There was no engine failure, no structural breakup in midair, no sudden weather event. The airplane was flyable until the moment it hit the ground. The official cause pointed to something both simple and uncomfortable. The crew had become so preoccupied with a single indicator light that they stopped doing the most basic job of all, which was to monitor the flight path. Tasks were not clearly divided. No one in the cockpit was assigned to do nothing but fly the airplane, while the others solved the gear problem. The automation change went unnoticed, the slow descent went unnoticed, and the alert that could have drawn their attention sounded where nobody was listening. On the morning of the 25th of September 1978, San Diego was under clear skies and busy air traffic. Pacific Southwest Airlines Flight 182, A Boeing 727 from Sacramento via Los Angeles was on final approach to Lindbergh Field. The aircraft had 135 people on board. Approach control and the tower were sequencing traffic into a single runway airport surrounded by city streets and houses. It was a normal day in Southern California, with jets turning in over the suburbs and lining up over the city for landing. A small Cessna 172 was also in the pattern that morning, flying a training flight with an instructor and a student pilot. It had been assigned to follow the 727 visually. Controllers cleared the Cessna to maintain visual separation, and they cleared PSA 182 to continue the approach after reporting that they had the Cessna in sight. At one point, the PSA crew did see the Cessna and called it out. But as the big jet turned and descended, the smaller aircraft slipped out of view under the nose and the right side of the 727. From that moment, the crew could no longer see it. But on the radio, they did not clearly say that the traffic was no longer in sight. The cockpit voice recorder later revealed a conversation that captures the confusion in real time. One crew member said, "I think he's passed off to our right." Another voice added, "I hope." There was a short discussion about where the Cessna might be, mixed with normal approach calls. Nobody in the cockpit demanded a firm answer. Nobody called the tower to say, "We have lost him." The approach continued. Outside, people in the neighborhoods below could see the two aircraft converging, but in the 727's cockpit, the smaller airplane was in a blind spot. At 9:01 local time, the Boeing 727 flew directly into the Cessna from behind and above. The right wing and nose section struck the smaller aircraft. The Cessna broke apart immediately. Fuel spilled and ignited around the larger jet. The 727's right wing was badly damaged, and the airplane rolled and pitched down. On the cockpit recording, the last words are a short, shocked phrase as the crew realized they had hit something. Then there is the sound of the stick shaker, warnings, and the rising noise of the impact. Seconds later, Flight 182 slammed into a residential neighborhood in North Park, exploded, and broke houses apart. All 135 people on the 727 and both occupants of the Cessna were killed, along with 7 people on the ground. Investigators concluded that several layers failed at once. The see and avoid concept did not work when one aircraft sat in the other's blind spot. The PSA crew did not clearly tell air traffic control that they had lost visual contact. The controller, assuming separation still existed, did not break off the approach. The phraseology used on frequency was casual and left room for misunderstanding. There was no traffic alert and collision avoidance system on board to warn the crews. The result was a high-speed mid-air collision just minutes before landing, not over open countryside, but directly above a dense city. PSA Flight 182 became one of the defining mid-air collisions of the 1970s. It pushed regulators and airlines toward stricter traffic pattern rules, more disciplined radio communication, and later toward mandatory collision avoidance technology for large airliners. For the people of San Diego, it also became a lasting memory. A clear morning when a jet on final did not just pass over the rooftops, but came down among them. On 28th of December, 1978, United Airlines Flight 173 was on the last leg of a long day. The flight had started in New York, stopped in Denver, and was now heading for Portland with 189 people on board. The aircraft was a long DC-8, a familiar workhorse on United's network. The final sector across the Rockies and into Oregon was routine. The weather around Portland was good for winter, with night conditions but no major storms in the area. According to the flight plan, there was enough fuel on board for the trip, the required reserve, and a margin for holding if needed. As the jet approached Portland, the crew were cleared for an approach to runway 28 left. The landing checklist was underway when something felt wrong. As the landing gear came down, there was a loud thump, a vibration, and a slight yaw. At the same time, the green light that should have confirmed the right main gear was locked did not come on. The pilots now had a puzzle, a noise, an odd feel in the airframe, and a missing indication on the panel. Unsure whether the landing gear was actually locked or damaged, the captain abandoned the approach and asked air traffic control for time to investigate. The controller cleared them to hold in a pattern southeast of the airport at 5,000 feet. The jet leveled out and began to circle over the suburbs. To keep the option of an immediate landing, the crew left the landing gear down and the flaps at 15 degrees. That configuration created a lot of drag. The NTSB later calculated that at 5,000 feet, with the gear down and flaps set like this, the DC-8 was burning fuel at roughly 220 pounds per minute. Every loop around the city was eating into the reserve much faster than it would have at a clean cruise setting. Inside the cockpit, most of the attention shifted to the landing gear. The captain wanted to be sure the leg was either properly locked or at least safe enough for an emergency landing. The first officer and flight engineer were busy running checklists, moving the gear lever, checking circuit breakers and watching indicator lights. They spoke with company maintenance by radio and discussed using the emergency extension system. All of this work took time, and during that time the fuel gauges continued to move in one direction. Fuel was mentioned more than once on the voice recorder. The engineer called out how many thousands of pounds remained. The first officer asked about the numbers and the time they had left. But both men did this in a careful, almost indirect way, trying to keep the captain informed without sounding alarmist or challenging his plan. The captain acknowledged the figures, yet his mental picture of the situation did not shift. He believed there was still enough fuel to keep holding while they briefed the cabin and made one more careful check of the gear. Outside the windows, Portland shrank and grew with each turn. Passengers saw the city lights drift past again and again. The cabin crew prepared everyone for the possibility of a hard or abnormal landing, collected loose items, and demonstrated brace positions. People assumed the danger would come when the wheels touched the runway. Almost nobody imagined that, above their heads, the greater danger was that the fuel needed to reach that runway was running out. After roughly an hour of circling, the fuel state had gone beyond tight and into critical. The jet was still at low altitude, still dragging gear and flaps through the air, and still burning more fuel than the original plan had allowed for. In the final minutes, the engines began to quit one by one. First, one of the engines on the right side flamed out, then another. The crew declared a mayday and turned toward the airport for an immediate landing attempt. The remaining engines were pushed to keep the aircraft flying a little longer. A few miles from the runway, over a dark residential area, the last engines died. The DC-8 lost power completely and began to sink. There was no time left for checklists or options. At about 6:15 p.m. local time, Flight 173 came down in a wooded area and residential neighborhood near East Burnside Street, around 6 miles southeast of the airport. The aircraft tore through trees and houses, broke apart, and came to rest in several sections. Because almost all of the usable fuel had already been burned, there was no large post-crash fire. Survivors later described the impact as a violent break followed by sudden silence, broken only by shouts in the dark. People crawled out through gaps in the fuselage and walked away onto the street, stunned and covered in debris. Out of 189 people on board, 10 died, and 179 survived, many with serious injuries. The investigation found that the landing gear itself was down and locked. A failed component in the gear assembly had damaged the microswitch that fed the green indicator light, making the cockpit display unreliable even though the leg was in position. The mechanical problem that triggered the hold was real, but survivable. The real cause of the crash lay in how the crew managed their attention, their communication, and their time while dealing with it. The NTSB's probable cause statement was blunt. The captain failed to monitor the fuel state and to act on the low fuel condition in time, and the other crew members did not communicate the seriousness of the situation strongly enough. The flight ran out of fuel because everyone in the cockpit was working, but no one successfully forced fuel to the top of the priority list. United Flight 173 became one of the landmark accidents in modern aviation. It showed that experience and technical skill were not enough if the culture inside the cockpit discouraged direct challenge and clear calls when something felt wrong. In the years that followed, regulators and airlines built a new training philosophy around this case. It was called crew resource management. The idea was simple. Everyone on the flight deck shares responsibility for the safety of the flight, and every crew member has both the right and the duty to speak up clearly, especially when fuel, flight path, or terrain are in doubt. United introduced one of the first formal training programs based on these ideas, and over time the same concepts spread around the world. On 10 September 1976, the sky over northern Yugoslavia looked calm. High above the fields and villages near Zagreb, a British Airways Trident and an Inex Adria DC-9 were crossing the same piece of airspace. Both flights were routine. Both crews were experienced. The weather was good, with clear visibility. There was no storm, no mechanical failure, and no warning in the cockpit that anything was about to go wrong. British Airways Flight 476 had departed London Heathrow for Istanbul earlier that morning. It was a Hawker Siddeley Trident 3B flying east along a busy airway at cruising altitude. On board were business travelers, holidaymakers, and a crew that had flown this route many times before. From the crew's point of view, the flight was smooth. They checked in with Zagreb control as they entered Yugoslav airspace and were cleared to continue at flight level 330, around 33,000 feet. At the same time, INEX Adria Flight 550, a McDonnell Douglas DC-9 charter flight, had taken off from Split on the Adriatic coast, bound for Cologne. Almost all of its passengers were German tourists returning from holiday. The crew requested a higher cruising level as they climbed inland. Zagreb's airspace, however, was divided into stacked sectors by altitude, each with its own controller. The middle sector controller agreed to let the DC-9 climb higher, toward the level where the Trident was already flying, and began to coordinate a handover to the upper sector controller. The Zagreb Control Center was one of the busiest in Europe at the time, but it was also understaffed and poorly equipped. Many flights crossed the same navigation beacon near Zagreb, and controllers had to keep track of them with limited radar tools and a high workload. When the DC-9 was passed from the middle sector to the upper sector, its transponder code was actually turned off as part of the handover, freeing the code for other traffic. On the upper controller's screen, the DC-9 stopped being a labeled target and became just another unmarked radar return among many. For a short but critical period, the controller knew there should be an Adria flight climbing, but he did not have a clear tagged symbol in front of him to show exactly where it was and what altitude it had reached. Radio communication then added another layer of confusion. The upper sector controller tried to sort out the traffic with short, hurried transmissions. He told the Adria crew to hold their present level and report when they passed Zagreb. The pilots, who had been cleared to climb, were not entirely sure which altitude he meant. They asked, "Which level?" The controller replied that there was another aircraft ahead of them at flight level 335 crossing from left to right, and he needed them to stay where they were. The DC-9 crew responded that they would remain exactly at flight level 330. It was the last clear message they sent. Only a few seconds later, the two aircraft met. At around 33,000 feet, closing at a combined speed of more than 1,000 kilometers per hour, the DC-9's left wing sliced into the Trident from below and to the side. It cut straight through the British aircraft's cockpit and forward cabin, killing the pilots instantly and tearing off the nose section. The front of the Trident broke away in an explosive decompression. The remaining fuselage, now without a flight deck, tumbled and fell almost vertically, trailing debris and luggage before crashing near the village of Gaj. The DC-9, missing a large part of its left wing, rolled and plunged into the ground near another village only seconds later. There were no survivors. All 176 people on both aircraft died. A Lufthansa 737 following behind saw a flash in the distance, and then two separate trails of smoke and debris falling toward the ground. The captain tried to report what he was seeing to Zagreb, but his first call was so shocked that the controller did not understand him. Only after several attempts did it become clear that two airliners had collided. In the control room, the upper sector controller kept calling British Airways 476 and Adria 550 over and over again, getting no reply. When the reality sank in, he slowly removed his headset and set it down. On the ground below, police, soldiers, and villagers rushed to two separate crash sites. Witnesses later described fragments of aircraft and suitcases raining down from a clear sky. The investigation found no fault in the weather, the aircraft, or the basic navigation route. Instead, it exposed a chain of human and systemic problems. Zagreb Center was overloaded and short on staff. The sector structure and handover process created moments when responsibility for the DC-9 was blurred. Turning off the transponder during the handover made the jet harder to track on radar, just when its altitude really mattered. Radio phraseology was not always standard. English was spoken with different accents and levels of fluency. Readbacks and hearbacks were not challenged firmly enough, even when there was room for doubt. There was no onboard collision avoidance system to warn the crews that their paths were crossing. The 1970s ended very differently from how they began. The jets were larger, the routes were longer, and the skies were much busier. But the biggest change was in how the industry thought about accidents. Each crash in this decade exposed not just a single mistake, but weak points in the whole system. Turkish Airlines 981 showed how one design flaw in a cargo door could destroy a widebody in seconds. Tenerife showed how fog, crowded runways, and casual radio language could put two 747s on the same strip of pavement. American 191 showed how a maintenance shortcut could bend a fitting and wait years to fail on takeoff. PSA 182 and the Zagreb collision proved that see and avoid was not enough in crowded airspace. Erebus showed how wrong navigation data and visual illusions could guide a modern jet straight into a mountain, even with all systems working. Eastern 66, Eastern 401, and United 173 revealed a different kind of danger. Storms that hid deadly wind patterns, and cockpit crews who became so focused on one technical problem or one light that nobody guarded the basics of altitude, fuel, and flight path. These events forced investigators to look past the last action in the cockpit and ask what in the design, the procedures, the training, and the culture had set the crew up to fail. From that came many of the protections we now see as standard: redesigned doors, stricter maintenance rules, better weather tools, ground radar, collision avoidance systems, and above all, formal crew resource management. The idea that everyone on the flight deck must speak up clearly about fuel, altitude, and risk is a direct legacy of this decade. By today's numbers, the 1970s were one of the deadliest periods in modern commercial aviation. But the lessons taken from those losses are part of the reason flying is so safe now. Almost every checklist, every call-out, and every briefing on a modern airliner carries a small piece of what was learned in those years. If you want more calm, detailed documentaries that go behind the headlines and explain how aviation really became safer, you can support the channel by subscribing and liking the video. It helps a lot and keeps these long research-based stories coming.